Just to let you know that I am recording this lesson. Obviously, for legal reasons, I need to make you aware of that. If yeah, I can see you've got your video turned off, so that should be fine. Just be aware if you put your video on, it's one that's going to be posted up for everyone to see. So we're going to have a look at molecular kinetic theory. So we're going to have a look at the behaviour of particles within a gas. So I'm going to switch first of all to my desk camera, and we'll start off with a basic. We'll start off with a very, very basic idea. The very basic idea to molecular kinetic theory is that we're looking at the behaviour of particles. Now, I think we've done this a little bit before, but I just need to be very, very clear. We need to start off with a very common question about the behaviour of particles in a gas, and that is what we call the 5 assumptions. There are several assumptions you can make, but the main ones that we make about gases is we assume that gases are made of particles and that the particles are moving in random directions. Now, when I say particles, I could mean atoms or molecules. So rather than saying atoms or molecules, I just use the word particles. So the particles move in random directions. So the motion is random. Remember, that's proven by Brownian motion. We're going to assume that those particles will collide. So we assume the particles collide elastically. So in other words, there's no loss of kinetic energy. If we think about it, that makes a lot of sense, because otherwise, if you had whoops, it does help if I spell correctly. If you think about it, if the particles collided with the walls and lost kinetic energy every time they collided, then the temperature of the gas would just keep going down and down for no apparent reason, and that doesn't happen. We're assuming that we've got many particles. We're going to assume a large number of particles, which means that the random directions kind of cancel each other out a little bit. We're going to assume the particles, the molecules or atoms, are very small, size is negligible compared with the distance apart. And that ensures that the gas does obey Boyle's law. Otherwise, the particles were very large, then you get to a certain point where the particles will all be touching each other and you couldn't compress the gas any further. So, and then the 5th assumption is going to be the idea that there's no forces between the particles. Okay, so the particles won't be attracted to each other, they won't be repelled by each other. We're just going to assume that they're almost like a rubber ball. So we start off with a basic idea. So if we start off with this basic idea, what we end up with, if I go to share my screen, what we end up with is a particle of a gas in a box, okay? Not really doing anything very interesting. Now imagine this box is a cube. If I set this simulation going, the particle moves backwards and forwards. Now if we think about it very carefully, what we could say here, if these are particles moving backwards and forwards, going from left to right, if we think about it, the particle is going to collide with this wall. We're going to consider a collision with this wall. There. Okay. Now, when the particle collides with that wall, what happens is that there is a change in momentum. The particle's got a momentum going off, let's say positive, and then leaves with a negative momentum. So there is a change in momentum. And that change in momentum means that there's an impulse and there's an equal opposite impulse on this wall here. So that impulse turns into a force if there's a continuous change in momentum. So we could think about how often this particle changes its momentum when it hits this wall. Well, in order to do that, the particle has to go once, and then twice the width of the box every time it hits this wall. Okay, doesn't matter if it's starting, say, from over here, or if it's starting from right next to where the wall is. Hits it once. So it has to collide once every time it collides. It collides once every time it moves twice the width of this box. So let's see if we can make a bit more sense of that. So the whole idea is that we need to consider the behavior of the particle as if it's in a box. So obviously we live in a three-dimensional universe. So let's imagine we've got a box like that, and like that. Let's say it's got a length x, a depth, we could call it z, and a height y. Okay, and the particle is inside there, and we're going to assume it's traveling with a component of its velocity in the direction of x. We're going to call that vx. Okay. Now it's going to cause pressure. It's going to cause pressure on this wall that I will call A. It's got a particular area. So as it collides, it exerts a force. There's a force over an area, which means that there's a pressure. Okay. So if we just take, first of all, a one-dimensional view of this, because we're going to ignore sort of the depth a little bit for a second. So if we take that one-dimensional view, particles moving with a velocity of Vx towards the wall A. It's got to travel to the wall, back again, and there before it can collide with this wall again. So the particle travels a distance of twice the width of this box. Travels 2x for each collision with A. So that means that if we know the distance x, we know this distance x, it travels 2x, that's the distance it travels. We know the speed. We can actually work out the time between collisions. Well, that's going to be given. That's using speed as distance over time. We know that therefore the time between collisions is going to be the distance, which is 2 times that distance x, divided by the speed in the x direction, the velocity of the particle in the x direction. That tells you the time between two collisions, the time between all the collisions. Okay, and that's an important formula which we'll come back to in very, very shortly. So if we do that, if we think about it, we can then work out the force, and we're going back really to our unit 2. Okay, so we established the idea the force on the wall, which we called A, is, well, the Newton's second law of motion says it is the rate of change of momentum. Okay, so if we think about it, it's going to be the change in momentum divided by time. So we know that the force on that wall A, so remember, we're thinking about our force here on this wall here. It's going to be applied every time this particle collides with that wall. So the force is the change in momentum. Well, momentum is mass times velocity. So if we think about it, a particle, well, we'll give it a mass little m for now, m for mass, and it's got a velocity of Vx. Okay. And then its momentum afterwards is going to be, well, the magnitude is going to be Vx, but it's traveling the opposite direction. So its velocity is minus V. So and as momentum's a vector, we have to think about the fact that the momentum afterwards has got to be minus Vx. Okay? If we think about it, when it's traveling in that direction, it's going to be minus V in the x direction. So the difference is the momentum minus m times Vx over the time t. So if we think about it, if that's the case, that gives us, that is a fairly simple thing. Well, if we've got a minus, if we're subtracting a negative number, it's the same as adding it. So m times Vx plus m times Vx is 2 times the mass times the speed in the x direction divided by the time taken. Quite useful. Now, we also know that the time taken, we've actually worked out before. That time is the time between collisions. So that is our time t. So we can use that formula substituting into here. So we end up with 2 times mvx over, so the formula we had here, whoops, cluttered desk, is 2x over vx. So it's going to be 2 times x over v in the x direction. And all we then do is just tidy it up. So if we tidy that up, we end up with, well, the 2 cancels with the 2. The Vx there, if you're dividing, if you've got reciprocal of a divided number, it just comes up to the top. So you've got mass times Vx times Vx again over x. And that gives you the force on that wall. Okay? So we're starting to get a much more elegant formula. But we don't really want to know about force. We're looking at sort of gas laws, which doesn't involve force, but it would involve pressure. Now remember, it's a force that's going to be over this entire area here. So if it's going to be over this entire area here, it's the force divided by the area of that wall, A. So the pressure is the force over the area. So if we use our formula for force from here, we end up with m Vx squared over x and also divided by the area. Now, if we look carefully at this area, we've got this distance x here multiplied by this distance area here. Now that's going to give you the volume. So this area times this distance will give you the volume of this sort of vessel. So we end up with the idea that x times A is equal to the volume. Okay, pretty simple, pretty simple. So if that's the case, then we end up with a pressure is equal to mvx squared over the volume of the vessel, or PV equals m times Vx squared. Okay, well that looks pretty good so far. So that's where we start for one molecule moving, for one particle moving in the x direction. But we've got 2 problems with that. First of all, particles don't just move from left to right, they move in random directions. So if I was to demonstrate that, particles move in random directions, okay? Now it takes a second to sort of settle down. They're moving random directions. They're not just moving from left to right, they're moving up and down. They're moving up and down in this case, and also moving in and out, which you can't see because you've got a 2-dimensional screen. So if we think about it, that particle, this only works for one dimension for one particle. So now we've got to think about a little bit got to think a little bit more carefully. Sorry, we're here, aren't we? So if we think about it, that's for one particle moving in one direction. We need to think a little bit more carefully. But we've got to remember, first of all, that we've got many particles. So we've got n particles, and we've got random directions in 3 dimensions. Okay, so that gives us 2 particular things, 2 particular cases where this formula starts to fall down. I think it's still an important one to know about because we'll come back to it. So if we think about it, there are 2 things to think about. Let's think about, first of all, 3 dimensions. If you've got a particle moving with a speed, which I will call c, that speed is going to have a component in the x direction that we looked at before. It's going to have a component in the y direction, and it will also have a component in the z direction. Okay? Okay, all these Vz, Vx, and Vy are all at right angles to each other. So it's a corner of a cube. So that C is basically the hypotenuse of a triangle. So if we think about it, to get C, we use Pythagoras' theorem. Only we use a 3-dimensional version of it. If we use a 3-dimensional version of it, then Vx squared plus Vy squared plus V velocity in the z direction squared, okay, that comes out to be the actual speed. But now we've got lots of particles moving at random. So the speed squared of all the particles moving in the x direction going to be the same as moving in the y direction and the z direction, because they're all moving in different directions. So we end up with the idea that Vx, that the average values for Vx squared is going to be the same as the average values for Vy squared and the same as the average values for Vz squared. Okay? So the idea is, because the particles are moving at random, if you look at the mean square speeds in any given direction, the component of mean square speeds in any given direction, they'll be the same. So they are the same. So our mean square speed, and just the square brackets basically means a mean square speed, gives you is like saying Vx squared. Now it'd be plus Vy squared, but Vy is the same as Vx. And Vz squared, which is also the same as Vx. So the mean square speed of all the particles is 3 times the mean square velocity in any given direction. Okay? So if we think about it, I can just tidy that up and say that's 1/3. Because divide both sides by 3, that's 1/3. Divide 3 by 3, it's itself. Multiplied by 1, it's the same thing. Now the reason why I do that is because we've got our previous formula. Our previous formula says PV equals mVx squared. So the pressure times the volume is equal to mass times Vx squared, which is 1/3 times the mean square speed. Okay, 1/3, not half, 1/3. There we are. Okay. So that's for one particle. But if every time you add a particle, you'll have more pressure because you have more collisions. So for n particles, we end up with PV is 1/3 times the number of particles times the mass of each particle multiplied by the mean square speed of the particles. Now, mean square speed is literally the average of the speed squared. So if you imagine you've got particles, you've got say 3 particles, and for each one, the speed, let's say, is 100 meters per second, 200 meters per second, and let's say 100 meters per second. You have to square the speeds first. So that's 10 to the power of 4. That's 4 times 10 to the power of 4. And that's then 10 to the power of 4. And then you average them. So we've got 10 to the power of 4, 6 times 10 to the power of 4. Add them together. You get 6 times 10 to the power of 4 divided by the number of particles, and you would have 2 times 10 to the power of 4, and that is the mean square speed. To get the root mean square speed, pretty simple. All you've got to do is square root that number. So you end up with 1.4 times 10 to the power of 2 meters per second. Okay, so that would give you the RMS value for the particles, the root mean square. So this is the mean square speed here, which is just basically you square the speeds and then you get the average of those squares. You then, to get the RMS, you have to square root it afterwards. Right, so we're taking that a little bit further. So this right here is quite a useful formula. Hopefully you can spot straight away its similarities. If we compare the formulae for a brief moment, that PV is equal to 1/3 nm times the mean square speed, with our equation of state that we're familiar with, the macroscopic properties, then the two things must be equal. Okay, we can start to tidy this up a little bit. We can start to see if there's a relationship between the speed of the particles, well, in this case, the mean square speed of the particles, and the temperature. So first of all, we can establish here, this is the number of particles and this is the number of moles. Now I happen to know that the number of moles times Avogadro's constant, it gives you the number of particles. That's something we've done before. So if that's the case, I can then substitute that in. That's 1/3 times number of moles times Avogadro's constant times the mass of each particle times the mean square speed, third, not half, equal to nRT. The number of moles cancel, okay? So the amount of gas has no effect on the temperature. And we can start to sort of play with this a little bit. Well, okay, well, if that's the case, the absolute temperature in Kelvin is going to be 1/3 times Avogadro's number times the mass of each particle times the mean square speed divided by Avogadro's constant, and the absolute temperature stays there. That's fine. Okay. Now, Avogadro's number is a constant, and R is also a constant. So it's equal to another constant, which we call K, which is the Boltzmann constant. Okay. Now, the Boltzmann constant, Avogadro's number, and the universal gas constant, those are given on your formula sheet on the exam, so don't worry about trying to memorize them, but I'm just trying to show you where it comes from. So we end up with the absolute temperature is 1/3 times the Boltzmann constant times the mass of each particle times the mean square speed of each particle. Okay, and that's quite a useful-ish formula, but it's not that good. But then, of course, because the reason why it's not very useful is because it doesn't really tell us very much, because we don't really know easily how to measure the mean square speed of the particles. But you can measure the kinetic energy, because that's because of the gas. That's going to lead to the internal energy. So the next thing to think about is to think about how we go about actually working out the absolute temperature. Well, we know that the kinetic energy of a particle, which I'm going to call E with a little k, kinetic energy of one particle is a half times mass times the speed squared. And it's because it's a mean square speed, it's the average kinetic energy of the particle, so we use the mean square speed to actually get that. And that's why we use the mean square speed, to give us an indication as to how fast particles are moving. So a classic example might be, would then be to work out what c squared is, what the mean square speed is from rearranging that. Well, it's the kinetic energy times 2, because we divide it by half, over m. So the temperature of a gas is a third times the Boltzmann constant times the mass of each particle. Then we substitute in our formula for c squared. So that's going to be 2 times the kinetic energy over the mass. Oops, I've gone off the bottom of the page. Okay, so the m's cancel. We can tidy this up a little bit. 2/3. We've got this right? No, that's 1 over the Boltzmann constant. I'll explain why in a bit, okay? Okay, it's 1 over k, which is then the kinetic energy of the particle. So to get the average kinetic energy of the individual particles, we rearrange that. That's 3 over 2 kt. That's why it's 1 over k, because I happen to know the numbers a bit different. Okay, and there it is. That gives you then the kinetic energy per particle. Okay, we can also, so what that tells you is that the absolute temperature is related to the kinetic energy of each particle. It's actually proportional. So if you double the temperature of a particle of gas, you're going to be doubling its kinetic energy. That's all right for one particle, but we don't really deal with a single particle of gas. So what we need to know is the internal energy of the gas. So that's the total energy actually stored inside the gas in its thermal energy. Okay. Now with the gas, there's no potential energy here, because there are no intermolecular forces. So the internal energy is basically the kinetic energy of all the particles in the sample of gas. So that, if we think about it, if it's n particles, and each particle has a kinetic energy of 3 over 2 k times the absolute temperature, then all we need to do is multiply that by the number of particles, and that gives you the internal energy of the gas. Okay. Now, if that's the case, well, we can start to look at the idea that internal energy, is equal to 3 over 2 nk times the absolute temperature. And there it is. It's that easy. It is honestly that easy. So do make sure you do know a little bit about the derivation. Now, what do you need to get out of that? First of all, the thing you need to memorize are the 5 assumptions. Questions on the assumptions to do with the particle gas are very, very common. The other thing you need to know is you need to know how to use, well, from the previous topic, you need to know the equation of state. You need to be able to link it, okay, to that formula. You need to be able to use the formula for the kinetic energy of one particle, and you need to be able to know the formula for the internal energy of a sample of gas. Whoops, 3/2, not 2/3. Having a senior moment there. Okay, you need to know you need to also understand that that is equal to 1/2 mc squared. You need to know that. You need to know how to use it. You also need to know the difference between the mean square speed. You need to know what the mean square speed is. Okay, the idea that it is the speeds squared added together, the sum of all the speeds squared. So you square each speed before you add them together and divide it by the number of particles, and understand also the root mean square speed, which is the square root of the sum of the particles squared divided by the number of particles, the whole thing square rooted. Okay, you do need to know that. You do need to know those particular terms. Any questions?
Thank you, sir. It's clear.
Okay, is there anything you need to know prior to the exam there, Arda?
About maths, so we have 6 topics, but we just did should be 4. We
right.
just did 4 topics,
Right.
and I'm worried because we can't 2 topics, and if I don't wanna, I can't do these 2 topics if I don't know the exam.
Right, that's a good question. Basically, you shouldn't receive anything in your exam that you haven't been taught. Now, the person really to ask about that, to be absolutely certain, would be, I'm not going to have you just stare at a blank screen. The person to ask would be your maths teacher. Ask them about it, and ask them what can be done about it. If you're not getting into that, who is your maths teacher, Arda?
Mr. Pradeep.
Mr. Pradeep. Okay.
Yeah.
So, why have you asked Mr. Pradeep about this?
I asked him before. He said we can't complete all topics. That's why I worry about it.
Right.
And next week next Monday I have a maths exam, and this term I'm really working hard, and I don't want to get a lower result.